now we find the time average power over one period of oscillation. Alright, for any given value of x, alright, which we can choose to be x equivalent to 0, right? And the average value of sine squared kx minus omega t over one period is equivalent to integration of the function, okay, to the respect of t with condition of 0 up to t period of time, right? Which is going to give us this solution. This is a product of integration sine squared omega t. Alright, and then if you substitute the limits here, you will get equivalent to half. Okay, so power average is equivalent to half rho A omega squared S max squared V. Right. So, and we know that the intensity is defined as the power per unit area, okay, as the rate at which the energy transported by the wave transfer through a unit area, okay, perpendicular to the direction of travel of the wave. This is the meaning of this equation. Let me show. A omega squared S max squared V over E. So the A is settled. So we are left with this equation. And intensity now is equivalent to delta P max. This one, actually delta P max square over 2 rho V. Right. And if we are specifically talking about sound wave, the intensity of sound wave, okay, let's say this is a source of our sound wave, loudspeaker, let's say our vocal cord. Alright, so we know that the sound going to travel radially, okay, going to travel radially from the source of it. Okay, so the wavefront of the sound wave going to be radially outward like this. Okay, the distance from one wavefront to another wavefront is 1 lambda. So we can consider this is let's say crest to crest, okay, or through to through. Okay, this is the ray or the wave that going to be propagate or transfer radially outward from the source. Because of the pattern of the sound wave is going to travel in radially outward like this, okay, so intensity is equivalent to power average over area. So the area right now is the 4 pi r square for a sphere, okay, because we have spherical wave like this. Okay, example 16.7, intensity variation of a point source. A point source emits sound wave with an average power output of 80 watt. Find the intensity 3 meter from the source. So make use of the last equation just now. Intensity is equivalent to power average over area, because we're talking about sound wave. It's a spherical wave, okay, radially outward. So the area is a sphere, for a sphere, which is 4 pi r squared. So you will get this is as your answer. And then part B, find the distance at which the intensity of the sound is this one. So rearrange the equation just now, where we have I equivalent to power average over the area. Okay, now we want to know the R, which is equivalent to power average over 4 pi r squared. So rearrange, our interest right now is the R. So you will have substitution of this one, okay, this is the intensity given, right? Then you will get R is equivalent to 2.52 times 10 to the power of 4 meter. Now we move to sound level in decibels. Example 16.6 just now. Okay, illustrate that the wide range of intensity to the order of power, very big, isn't it? The human ear can detect. Okay, because this range is so wide, all right, now it is more convenient, okay, for us to use logarithmic scale. Okay, the logarithmic scale here is known as or named as sound level, okay, which is beta, symbolized as beta. This is sound level, okay, in decibel. Actually, we are making use logarithmic scale. So what is sound level in decibel is defined as beta, equivalent to 10 log, okay, I over I naught. Okay, I naught here is a value of 1 times to the 10 to the power of negative 12. This is actually threshold of hearing. This is the weakest intensity that human can hear. That is why the name of it is threshold of hearing. Right, this is threshold of pain. This is the highest intensity that human can tolerate. Is bigger than this, then it's going to cause pain. Now, if let's say we want to have intensity, the sound level that the highest we can receive, or we can adjust for our hearing system. Let's say we put a threshold of pain to this one, which is our I, to the respect ratio to the I naught threshold of hearing, you will have 120 decibel. Alright, so 120 decibel is the siren, rocket concert. So it's going to be pin. Right, then if we are talking about sound level for the threshold of hearing, so substitute this one to this as I over I naught itself. Okay, we will get 0 decibel. Okay, this is the weakest that human can hear, right? So threshold of hearing, just rustling of leaves equivalent to 10 decibel, whispers 30 decibel, alright, and so on. So example 16.8. Now, two identical machines are positioned at the same distance from a worker. The intensity of sound delivered by each operating machine at the worker's location is this amount. A. Find the sound level heard by the worker when one machine is operating. So the intensity produced by the machine, okay, substitute into this equation over the I naught, the threshold of hearing, you will get 53 decibel. Part B, find the sound level heard by the worker when two machines are operating. So when you have two machines now, you are going to double the intensity of the machines. Okay, you will get 56. If you see here, it's not directly double compared to the part A, isn't it? Because it's based on the logarithmic scale. So it's 56 decibel for two machines. Example 16.8. Okay, loudness is a physical response to a sound. It depends on both the intensity and the frequency of the sound. As a rule of thumb, a doubling in loudness is approximately associated with an increase in sound level of 10 decibel. This rule of thumb is relatively inaccurate at very low or very high frequency. If the loudness of the machines in this example is to be doubled, how many machines at the same distance from the worker must be running? So our aim, okay, the loudness to be doubled. Okay, so from the statement given here, beta 2 minus beta 1, the difference in, okay, is equivalent to 10 decibel. Right, and what does that mean by this? This is actually the process of it. Okay, is equivalent to 10 log. Okay, you can have in term of I2 ratio to, it's minus, right? So 10 log I2 ratio to I1. Okay, so rearrange this one. Okay, remember this, the whole part of this equivalent to 10. So rearrange the equation, you will get I2 equivalent to 10 times I1, right? So it means that you are going to have 10 machines operating. Okay, then you are going to double the loudness. Okay, so this is the list of the loudness and frequency, sound level, okay, infrasonic, sonic frequency, ultrasonic frequency. So you can see here lots of, alright. So certain animals, okay, for example bats, okay, are using ultrasonic frequency, okay. Cockroach, infrasonic, if I'm not mistaken. Okay, so here we have birds, okay, rock concert rifle, threshold of pain is here, alright. Then next one is the Doppler effect, right. The Doppler effect is actually a phenomenon whereby the heard frequency by the observer is different compared to the real frequency coming from the source of the wave. Okay, this is due to the relative motion between the observer and the wave itself. For this example, it's talking about the different relative motion between the observer and the wave. Let's imagine you are in a boat that is lying at anchor on a gentle sea where waves have a period of 3 seconds. Hence, okay, every 3 seconds a crest hit your boat. Okay, in figure 16.23a, this one, okay, shows this situation. Okay, with the water wave moving towards the left, okay, and then after that, if you set your watch to t equivalent to 0, just as one crest hit, the watch read 3 seconds. When the next crest hits, 6 seconds will when the third crest hits, and so on. Right. From the observation, you can conclude that the wave frequency is f equivalent to 1 over t. Okay, which is equivalent to 1 over 3, which is equivalent to 0.33 Hertz. Okay, now suppose you pull up your anchor, right, for this case, okay, and then you start your motor and head directly into the oncoming wave. So means that you're going to move to the right because the wave is moving to the left. When you are heading to the oncoming wave, you are moving against the direction of the wave motion, right? Again, you set your watch, okay, at t equivalent to 0, okay, as a crest hits the front, the bow of your boat. Now, however, because you are moving towards the next wave crest, okay, as it moves towards you, it hits you less than 3 seconds, faster, right, supposedly, okay, after the first hit. In other words, the period you observe will be shorter than this one. Because of f equivalent to 1 over t, okay, you observe a higher wave frequency than when you are at rest. If you turn around, okay, for this case, and move in the same direction to the wave direction, okay, you observe the opposite effect. You set your watch to t equivalent to 0 as a crest hit the stern of your boat. Because now you are moving away from the next crest, more than 3 seconds has elapsed on your watch by the time that the crest catches you. Okay, therefore, you observe a lower frequency than when you were at rest in comparison to the case A. Okay, this effect occurs because relative speed between your boat and the wave, okay, depends on the direction of travel and on the speed of your boat as well. Okay, when you are moving towards the right, in this case, this relative speed is higher than that of the wave speed, which leads to the observation of an increased frequency. When you turn around and move to the left, okay, in this case, the relative speed is lower and is observed frequency of the water wave. Okay, so this is actually the same thing happen, okay, for sound wave, okay, as well, where the relative motion between the observer and the wave itself going to vary the frequency. Okay, so the same goes to the sound wave, all right, because of the relative motion between the observer and the source of the wave, okay, we are going to have a hertz frequency varied according to the relative motion between these two. All right, so this is the equation whenever the observer moving towards, whenever the observer moving away from the source, and etc. Okay. Why is it happening like that? Because of the lambda. Okay, the wave front, okay, the distance traveled by the wave is different or varied due to motion of the observer and also the source. Okay, so by using this information, we can substitute it to this, okay, and then finally we get this one. So you have lots of equation, but madam have conclusion of it, okay, where we're going to come up with a conclusion which is easier, which is this one. Okay, in this equation, okay, the hertz frequency by the observer is equivalent to the speed of the sound in air, right, plus minus, okay, could be plus, it could be minus depending on the situation, v of the observer, okay, over v of the sound in air, okay, minus, it could be minus, it could be plus, but normally it's going to opposite normally. Okay, if this one is plus, this one going to be not minus normally. All right, minus or plus v of the source, okay, bracket everything here times with the original frequency coming from the source. So how to select whether the sign for V observer and V source here positive or negative? Okay, take a look on this. For observer, okay, if it is moving towards the source, okay, our relative motion only observer and source, right? So it doesn't matter to the left or to the right, okay, for this case. So for V observer, if it is moving towards the source, okay, then you're going to use positive sign for the speed of it. If it is moving away, you're going to use negative sign. If it is static or remain at rest, okay, then you're going to put it as 0, the V of the observer. For the V of the source, okay, for towards motion to the observer, you're going to use negative sign for it. If it is moving away from the observer, you're going to use positive sign for it. It's opposite. Okay, it's opposite. But if it is static, it's the same. The V going to be 0. So let's apply that equation into this example. Okay, your clock radio awakens you with a steady and irritating sound of frequency 600 Hz. One morning, it malfunctions and cannot be turned off. In frustration, you drop the clock radio from the rest of your 4th story dorm window, 15 meters from the ground. Assume the speed of sound is 343 meters per second. As you listen to the falling clock radio, what frequency do you hear just before you hear it striking the ground? Okay, first thing first is involve free falling case because you drop your clock, right, your alarm. So Vs, okay, of the your alarm, your clock just now, okay, equivalent to Vy initial plus Ayt, Vy equivalent to 0 because you release it from rest, okay, and why is it minus Gt? Because it's free fall, falling down, so the A equivalent to negative G. Then delta Y equivalent to Vyt, Vy initial T, plus half Ayt square, your Ay negative G. And we know that initially it started at origin as our reference point, so initial position 0, V initial along Y as well 0 as well because it's drop, okay, and your Ay equivalent to negative G. From here you're going to solve for your T, right, and substitute this T into your Vs, right, then you are left with this, simplified with this. Now this is your V source, right, your alarm, your source. So the hertz frequency by U is equivalent to V. Originally you have hertz frequency is equivalent to V of the sound plus minus V of the observer over V of the sound. It could be plus minus as well, okay, V of the source times with the frequency of the source. So now which sign we are going to use? We see you are, as the observer, you are stationary, right? You are stationary, so this one going to be 0 because you are stationary, right? So what about your source? Your source is moving away. If it is moving away, okay, moving away, so you are going to use positive sign, okay, positive sign of your Vs. So remember your Vs is this one, right? So positive sign, if you substitute here, you see this is the meaning of positive sign just now, okay. If you refer to this solution, is using the previous equation that they use or derive, the book derive. But this is the one that madam conclude for you. So now if the source is moving away, you are going to use positive sign. So this is your Vs, got negative sign, right? Okay. And then this is the whole bar of this is your Vs. The whole bar of this. This is your Vs. V source, right? So when you substitute it into this equation, okay, you see you're going to use positive sign, not negative sign, right? Because it's positive sign, okay. And your displacement is downward, right? So it's negative 15 times with negative here, you will get positive answer. This is the received frequency or heard frequency by you as the observer. Now example 16.10, Doppler submarines. Okay, a submarine sub A travels through water at a speed of 8 meter per second, emits a sonar wave at a frequency of 1400 Hz. The speed of sound in the water is 153 meter per second. A second submarine sub B is located such that both submarines are traveling directly towards each other. So the keyword is towards each other, right? The second submarine is moving at this, right? Okay. So the question, what frequency is detected by an observer riding on sub B as the subs approach each other? So received by sub B, okay, received by the sub B. So means that the sub B going to be the observer, the submarine A going to be the source, right? So by make use of Doppler effect equation, right? So let's begin with the general one, right? F received by the observer P is equivalent to speed of sound, okay, in C, in water, okay, V of the observer, which is the B over V of the source, which is the sub A, F of the A, right? So which sign to be used, positive or negative? So let's take a look. The submarine is moving towards each other, right? Therefore, okay, for the V observer, okay, the sub B, okay, observer is moving towards, so it's going to be positive, right? And then the source is also moving towards, going to be negative. So it's tally with this, right? Okay, and then it's tally with this. Okay, you will get this is as your answer, right? Now, the sub B barely miss each other and pass. What frequency is detected by an observer riding on sub B as the subs recede from each other, so moving away from each other? Okay, so for this case, right, again, madam going to do it in my way. Okay, who is going to be the observer? B, right? Okay, because the question is what frequency is detected by the observer riding on sub B. So the B going to be the observer or the one that receive the frequency. So here going to be VB, right? And here going to be VA as our source. So F here, F from A as our source. Right, so observer is moving away. Okay, both of it moving away. So observer moving away. So negative sign. Alright, and then the source is moving away as well. Positive sign. Right, so don't look at this. Look at this one. Okay, so you will get here negative, right? Here is positive. It's easier. My method is easier. Because you are using textbook method, you also need to consider the direction of the V for each of the submarines or observer and also the source. Okay. Okay, for part C, while the subs are approaching each other, some of the sound from sub A reflects from sub B and returns to sub A. Okay, if this sound were to be detected by an observer on sub A, what is its frequency? Okay, so the receive frequency, now the symbol is double prime. Okay, then the source of frequency of the source is the F prime, the one that heard, because it's being reflected at B and then received to A, isn't it? So the heard frequency by the observer in submarine B going to be the source, okay, that received by the submarine A. Okay, so by make use of F, okay, equivalent to V observer over V source times with the coming from reflected one. Okay, so it is approaching each other, right? Approaching each other. So the V of the observer is towards positive. And then the V of the source also moving towards, going to be negative. Right. So if you see here, okay, it's going to be positive. It's going to be negative. easy, right? So the one that you are using here is this one, 1416. The F prime that you use here, 141, which is the F reflected by the sub B as our source to be detected on the submarine A. So your final answer 1432 Hz.